All right. Um, now that we have made a bunch of connections between translational or linear motion and rotational motion, we're ready to make our final connection, and that is the connection between momentum in linear translational motion and angular momentum with rotational motion. And so the idea here, just like we introduced with angular motion, we've got an object going around in a circle, so you can describe the distance r from the center of the circle. You can talk about that translational velocity, which of course is connected to a momentum, right? Just multiply by the mass of the object and you get the momentum. And so we can define the angular momentum as this vector quantity, which is the cross product between r and the momentum vector, which again is m times v. So it's really r cross v. And so that is the angular momentum. So it not only takes into account the linear momentum of the object, p, but also how far away that object is located from some axis point, some point of interest. And typically, you'll be looking at things that are rotating or orbiting, and so this radial distance here is sort of out from the center. Now, since this is a cross product, that means L is perpendicular to both R and P, and then the magnitude of the angular momentum is just like any of our cross products, the magnitude of R multiplied by the magnitude of P, and then multiplied by the sine of the angle between the two vectors, right? So that's what theta is corresponding to, the angle between R and P. Now, just like in translational motion, when we were talking about momentum, if you take the time derivative of the momentum, you get, it's essentially related to the net force on the object, right? The time derivative of P here is ma. And so just like you can do that for translational motion, you can do that here with rotational or angular motion. So if you take the time derivative of the angular momentum, that's related to the net torque on the object about the axis that these angular momenta vectors are defined. So the total angular momentum of a system is just denoted with a capital L, and it would just be add up all the individual angular momentum vectors for all the different objects that are in your system that you're considering. And so notation-wise, then take the time derivative of the total angular momentum, so this capital L vector, that's equal to the net torque about your axis that you've defined to discuss or describe the total angular momentum. Now, for a rigid body, the angular momentum is defined as I omega. So for rigid bodies, we can determine the moment of inertia. And so multiplying that moment of inertia by omega, the angular speed or angular velocity, that gives you the angular momentum. And so the big picture, big story, same reason why momentum turned out to be so useful is that there's a conservation law associated with angular momentum, just like there was with momentum, and that is for your isolated systems, the total angular momentum of a system doesn't change. So at any time, the total angular momentum will be the same value. So that could be written as, take the derivative with respect to time, that's equal to 0, or that the total angular momentum, which equals add up all the terms, is some constant value. Now, this conservation of angular momentum has a whole suite of applications that you have seen or have experience with on a day-to-day basis. Some of the most popular examples include figure skaters. So when figure skaters, and we'll watch a video in class, when figure skaters are doing their spins and they have their arms and legs out, they are rotating with some angular speed, and then the distribution of their mass defines some moment of inertia about this axis of rotation. And then as the skaters pull in their arms and legs so that there's less distance from the rotation axis to the rest of the mass of the body, then the angular speed will increase, because the moment of inertia, as you move all of the mass closer to the rotation axis, the moment of inertia goes down, but this quantity I omega has to stay constant. So if I goes down, omega has to increase. And so we bring our arms and legs in, moment of inertia goes down, but omega, the angular speed, goes up, and so you'll see the skater spin faster and faster and faster as those arms and legs come in closer to that rotation axis. What's really cool is, as an astronomer, there are some very popular examples of conservation of angular momentum. One of the most common to talk about is the fact that stars form from large molecular clouds that have maybe some small rotation at the start, and then due to gravity, these clouds begin to collapse, and as they collapse, more and more mass gets closer and closer to the axis of rotation, and so the moment of inertia is going down, the angular speed will be increasing, and so what you end up getting is you get some ordered rotation as this system forms. You get some ordered rotation where, in terms of a solar system or a star system, the main central object ends up being the most massive, and then all of the material that didn't make it into the main star gravitationally interacts and begins to form little objects that, again, due to the conservation of angular momentum, are rotating in the same direction as the system was originally. And so this is where the planets come from. So you get some typically dense, hot object in the center, star, and then you get less massive objects like planets outside in orbit around, and in a variety of star systems you end up getting more than one star, because maybe you get your central star here, and then maybe something like Jupiter, instead of it being a planet, actually has enough mass to form a star where there's fusion happening in the core. So again, the conservation of angular momentum is essentially responsible for this system not only flattening, but also spinning up as the large or giant molecular cloud, which has some small net rotation as it gets smaller and smaller in radial size, speeds up or spins up. And so we're going to look at an example here. This is a very popular conservation of angular momentum example. The idea of a star, which in this case it's our sun, a star rotating with some angular speed, and then that star collapses down into a star with smaller radius, and the star spins up. And so this is sort of a natural evolution for a star's life cycle. So something like our sun, which is about 5 billion years old now, when the sun reaches about 10 billion years old, there's going to be a variety of changes that take place, and eventually what's going to happen is the sun, which has a radius of about 7 times 10 to the 5 kilometers, the sun is going to collapse down to a radius of about 3.5 times 10 to the 3 kilometers. And so what we want to do here is we want to figure out all right, if the sun is got a rotational period of 28 days today, well, when it collapses down into this, packs all of the mass into this smaller radius, how fast will it be rotating at that point in time? And so the picture here is right now the sun, very large radial extent and rotating at a certain rate, is going to collapse down into something very tiny. What's the rotation rate after that collapse? And for this particular problem, we're saying that all of the mass that's in the sun today makes it into, basically gets crammed into this smaller sized object. So here are the things that are provided in the problem. We're told the radius of the sun currently, we're told the mass, we're told the period. So the period is roughly 28 days. And so what I'm going to do is I'm going to go through how to calculate the angular momentum of the sun today, and then we're going to compare that to the angular momentum sometime later, and that'll allow us to find the speed after it's collapsed. So to find the angular momentum, I want to figure out omega, so that definition is 2 pi over the period. So if I just plug in the period here, I get that the angular speed is about 0.224 radians per day, and then I'm just going to convert that into radians per second right here, 2.6 times 10 to the minus 6 radians per second. The other thing we know about the sun here is that we're going to treat it like a sphere. Well, a solid sphere rotating about any axis is 2/5 mr squared. So if I plug in the mass given here and the radius given here, plugging in meters rather than kilometers, I get this for the moment of inertia of the sun today. And so before the collapse, if I want to calculate the angular momentum, all I'm going to do is multiply I and omega. So I'm just going to multiply these two numbers together. And that's where I get this value. So that's the angular momentum before collapse. And now, after the collapse, well, the radial extent is significantly smaller. And so after, still the same moment of inertia expression, still the same mass, but now r is different. And so I get a different moment of inertia. Again, that's because more of the mass is closer to the rotation axis. And so you'll notice that 10 to the 42 versus 10 to the 47. So the moment of inertia has gone down significantly. And so what we should expect is that the angular speed should be much higher, which would correspond to a smaller period. So afterwards, I omega, so I don't know what omega is after, but I know what I is because I just calculated it. And that, again, is the angular momentum after. It's got to be equal to the angular momentum before, so I'm setting that equal to this number right here. So then I solve for omega after, and I get 0.104 radian per second. And now if I want the period, I just got to take 2 pi over omega, and I get that the period is about 60 seconds, it's about a minute. So after the sun collapses down into this white dwarf star, the orbital period, or the rotational period, will be about a minute, whereas right now it's about 28 days. And so all of the mass getting scrunched down into this smaller radius means that the star's got to be rotating faster and faster, right? Because the thing that's constant is the angular momentum. So since I is going to get smaller, omega's got to get much bigger.